All right, this is the second topic in Unit 3, and it's determining the degree of a polynomial. So example 2 says, for each of the following polynomials, determine the degree of the polynomial, find all real zeros, and state the multiplicity of each zero. So what I talked about in the last video was seeing polynomials in standard form versus factored form. We want to get all of these polynomials in factored form so that we can easily see the zeros and their multiplicities. Now, part A, it's already in factored form, so we don't need to factor anymore, and we can just see what the degree is and what the zeros are and their multiplicities. For the degree, I want to think of distributing all of the x's together. So I have x cubed times x, which is x to the fourth, and then I have over here technically x squared, because if I expand that binomial, the leading term is x squared. So we have x cubed times x, which is x to the fourth, times x squared, which is x to the sixth. So we have a degree 6 polynomial. For the zeros, get this out of the way. The first zero is x equals 0 with a multiplicity of 3, because it's raised to the power of 3. So it has a multiplicity of 3. So when it crosses the x-axis at 0, you're going to see that slide. I'm not sure if it's increasing or decreasing there, but it will create a slide nonetheless. The next 0 is x equals -1, and this has a multiplicity of 1, because the binomial is raised to the power of 1. The last 0 is going to be x equals 4 with a multiplicity of 2, because it's squared. All right, part B, we'll do the same steps that we did for part A. This one is almost fully factored, but we have perfect squares in here, or a difference of squares. So we'll rewrite this as 3x minus 2, x plus 2, times x minus 2 to the power of 4. And to see the true multiplicity of each of the zeros, we need to combine when they are the same. So we'll have 3 times x minus 2 raised to the fifth times x plus 2. So again, we have another degree 6 polynomial, because I can see this x here. Technically, it's x to the fifth if I expand all of this and multiply those out. And then we have another x, so it will be x to the power of 6, so degree 6. For the zeros, the first 0 is going to be at x equals 2 with a multiplicity of 5. The next 0 is x equals -2 with a multiplicity of 1. And part C. So part C, we have two trinomials. They're both factorable, so we're going to factor each one separately. The first one, the greatest common factor, is going to be x. So we'll factor out the x. So we're left with x squared minus x minus 6. And then we can factor that again. Two numbers that multiply to -6 but add up to -1 will be x minus 3 times x plus 2. For the second trinomial, sorry, that's my dog, we can use two numbers that add up to 12. Multiply to +12 but add up to -7. And we can use x minus 3 times x minus 4. And we'll continue that down here. So again, we have two binomials that are the same, so we can combine them. So we'll have x minus 3 squared times x plus 2 times x minus 4. And now we're finally in the fully factored form of this polynomial. So for the degree, if we go back to the original, we have a degree 3 and a degree 2. If we expand and multiply those out, we have a degree 5. For the zeros, We have 4 zeros total, and 3 of them have a multiplicity of 1. So I'm going to do x equals -2, 0, and 4 with a multiplicity of 1. And then we have x equals 3 with a multiplicity of 2. All right, another way to determine the degree of a polynomial is through a table. All right, so with these tables, think back to rate of change. We really like when the inputs are equal length input intervals. All right, or in this case, the change is going to be 3, which means the x values are changing by 3. Okay. This is okay for polynomials. For average rate of change, we always wanted to do the difference in the y values divided by the difference in the x values. Because these are the same, you can go, because the x is changing consistently, +3, +3, +3, we can go ahead and just focus on the distance between the outputs. Now, if they were not the same, like we went from 0 to 1 to 5 to 9 or something like that, then we would need to use our difference quotient or use the actual average rate of change. Somebody asked me, can we just always do the average rate of change so that we're not playing the guessing game? The answer is yes. If you want to play it safe, you can always just do the average rate of change when determining the degree of a polynomial, concavity, if a table of that, if looking at a function through a table is linear versus quadratic or neither. If you always do average rate of change, that will bring you to the correct determination for that. So for this one, I'm not going to because delta x is the same. So from -2 to 0, I'm adding 2. From 0 to 10, I'm adding 10, add 17, and then add 23. And if you think back also, we talked about common differences. This is my first common difference, okay? So this is definitely not linear because it's not the same. So now we're going to go to the second common difference. So we're adding 8, add 7, add 6. This is our second common difference, which means it is not quadratic. So we'll try one more. We subtracted 1, we subtracted 1. This is our third common difference, and it's the same. So this is going to be a cubic polynomial. So the degree of the polynomial is 3 because the third differences are constant. And I didn't say justify, but it's good practice to just justify everything. All right, the next one, if we take a look at the x values, we're adding 2 each time, so we don't have to use the average rate of change. Okay, we can just focus on the outputs. Now for concavity, you should always use average rate of change because we have to see if the average rate of change is increasing or decreasing or not changing. But for the degree of a polynomial, if delta x is the same, we can go ahead and just focus on the outputs. So if we look at the outputs, we're going from -2 to -3, so we subtract 1. -3 to -2, we add 2. Sorry, -3 to -1. -1 to 4, we're adding 5. And then 4 to 12, we're adding 8. So it's not linear, it's not going to be x. So let's try the second one. So from -1 to +2, we're adding 3. 2 to 5, we add 3. 5 to 8, we add 3. So now, second common difference, we have a quadratic. So the degree of the polynomial is 2 because the second common difference is constant. All right, hope this helps.